Welcome to Data Skeptic Time Series.
This is Data Skeptic Time Series, the podcast about how to predict the future based on historical sequential data. Episode number. A number of neural network approaches have been applied to time series forecasting. In almost all of them, a deep architecture must be defined, often from a common template. The training of that network results in a predictive model. Some of these neural network approaches, such as the one we'll be discussing today, also bear the accolade of being interpretable. The Neural Basis Expansion Analysis for Interpretable Time Series, or NBEATS for short, achieves state-of-the-art results when first published for a set of well-known datasets. Today on the show, I speak with Boris Oreshkin about this topic.
Hello everyone, my name is Boris. I'm a senior research scientist at Unity Technologies and I work on deep learning for animation at Unity.
Well, before we get into our main paper, I would love to maybe ask you for a little background on that. I'm aware of Unity as a very popular game system. If someone were a game developer, how might they be benefiting from some work like the things you're doing there?
Right now we are designing systems for UX experience to make the design of animations and the character poses much easier and faster. But I guess the NBEATS paper was written when I was applied research scientist at Element AI, so it was a completely different experience, I would say.
But with some commonality in deep learning, I guess.
Yeah, that's for sure. And Element AI was working on a wide array of problems, and a subset of those problems was the problems related to time series forecasting.
Definitely. So I've seen several approaches over the years to trying to combine deep learning with time series, or more broadly, machine learning with time series. But this paper, NBEATS, presents a couple of unique ideas I had not encountered before. For example, one of them being it really doesn't take anything from traditional statistical approaches. It's sort of a purely deep learning methodology. Was that one of the major goals when you guys set out along this course?
Exactly, because one of the famous guys in the time series domain is Spiros Makridakis, and he has been organizing those M-series competitions for a long time. And I think early on when the competitions started, the data sets for those competitions were small, and fitting larger models wasn't viable. And also the time series models were used in a very classical way, meaning that there is one time series. There is a model or a bunch of models that are known to work well. And the model is fitted on that one time series, and we expect it to produce very good results. But deep learning works in a completely different way. It really needs to train over, multiple time series or multiple examples. And this is, I think, the main thing that kind of differentiates the NBEATS approach. And pretty much, the problems that Makridakis at some point outlined that, machine learning and deep learning were not at all successful at time series tasks. They were actually mainly related to the fact that people used machine learning models applied to time series in the way that those models are not supposed to be used. So the machine learning model is not supposed to be used on one single time series in isolation. And really to get the most out of it, you have to train it on a collection of time series, and then you apply it on a collection of other time series, that you wanted to test on.
Yeah, this was an idea that's very interesting because, for me at least, it began as a kind of contradiction to what I was thinking. I always thought, well, time series is so broad, there's every possible time series problem. Surely I should just train on only my data set because who knows, how could there be applicability from farming data in, computer CPU data or something like this? But that didn't seem to be the case. How do we get a benefit from taking a broad sampling of time series?
If you take the M4 competition dataset, we have different subsets. So some of them are monthly, some of them are yearly, some of them are hourly, for example. And if you take a look at those subsets of different time series, we see that the time series, each of them is unique, but at the same time, they really share a lot of commonalities. So for example, monthly time series, typically you'll see cycles over the year. So like something happens in winter and doesn't happen in summer, or like quarterly time series, it's like the same thing, like all those things that tend to happen during certain quarters and not the others. So you see a lot of patterns that look like quasi-periodic waves. And for sure, there is a lot of noise in each of those time series, but the model essentially learns that for monthly time series, there is this like 12 months, for example, seasonality. So I can get away internally creating estimates of that seasonality, amplitude and shift. And then I can, when I see a different time series that is from the same domain, I know that what I need is to get, the phase offset of that time series and the amplitude and all of those things, combine them together, and I can get a good forecast for this particular time series. So the model learns how to understand those time series when it sees a lot of them. And I think one other interesting thing about that is that, so like you mentioned before, that there was a pure deep learning model applied to time series and it was successful. So it was like a major thing to kind of inspire people move more in that direction. But the other thing that we did is that we actually showed that you can do a decomposition into trend and seasonality, where trend is like quasi-monotonic and seasonality is quasi-periodic. And then the model pretty much is forced to output the parameters of that trend and seasonality, and it still works. So it means that the model actually learns, it can learn to estimate parameters just the same way as the regular time series models do internally, but it does it in a more like adaptable and flexible way, because it learns how to do those estimates directly from the data set instead of using heuristics provided by the humans. And so under the assumption that when we test, the time series still come from a similar distribution, it's highly likely that that estimation procedure learned by the model from the data will be more optimal than a heuristic model that was proposed by a human.
One criticism people have about deep learning approaches is that they can be black boxes, that although they solve the problem, it's not easy for someone to understand how they're working. Could you talk about some of the ways you addressed those concerns in the design and architecture of NBeats?
Yeah, exactly. I guess it's related a little bit to what I said previously, that there was a model that was purely learned in all the layers. And then there was another thing that we proposed is the interpretable version of the same model, where the output layers are fixed by a human, let's say, designer. And then those output layers, they have a very well-defined form of either trend layer or a seasonality layer that is parameterized very similarly to how the usual trend and seasonality models in classical approaches are done. And then we see that the model can output the estimates of trend and seasonality parameters, and those outputs can be interpretable by humans very easily. So it looks a lot like that decomposition into trend and seasonality that is often used by time series practitioners.
Yeah, so very familiar to people who know techniques like ARIMA and that sort of thing. So slides right in, even though it's fundamentally different, which is interesting.
Exactly.
One thing that NBeats does that is a kind of popular approach I first learned in natural language processing is both the forward look ahead and the backwards look back process. Can you talk a little bit about how that architecture allows the system to better learn the time series?
Well, first of all, this is directly related to the ideas of residual deep neural architectures, which are like extremely popular right now in any domain you can think about. The image processing and speech processing and NLP, it's like everywhere. And it works so much better than stacking the layers without those residual connections. And I guess for people unfamiliar with the deep learning field, what those residual connections are doing, they greatly improve the learning process of the model by simplifying the propagation of gradients in the learning procedure. And also at the same time, the idea of those backcast links didn't really come from the deep learning background, because I was doing at some point a lot of signal processing, and on biomedical data, which is often tends to be time series, there was a lot of parameter estimation from like waveforms and decomposing those waveforms and trying to use things like splines to filter out components that you don't want before you do Fourier transform and look at the spectrum and do some decision making in that space. So what I learned from that experience when doing signal processing is that when you do some kind of analysis of the signal, it often helps to kind of decompose it in components of different frequencies. So like, for example, if you want estimate of pulse rate and you have a signal that is corrupted by movements of the sensor on the skin, then first of all what needs to be done is removing slow and trend like components. So like you have some function that could, for example, estimate a spline from the waveform, subtract it from that waveform, and then it kind of cleans the spectrum a lot so that you don't have that Gibbs how is it called? I even forgot. It was like so long ago. Like the penetration of the unwanted strong components through the side lobes of the like Fourier filter transform. And so like you remove the strong signal, it doesn't penetrate through those side lobes, and then you can do analysis of a much cleaner spectrum. And so that's exactly the same idea here. First, I try to use like convolutional networks and feed them to that problem. And then it didn't really work all that well. And so I thought maybe the problem is that, like those trends and whatnot, they are hard to catch using convolutions. So let's try to clean up the signal and like subtract all those things. What happened first? I added the layer, that estimates the parameters of the trend and subtracts the parameters like the estimated trend from the input window and output window. And then we do like convolutions after. And so it suddenly worked so much better, but wasn't still, close to where we wanted to be. And so I decided, maybe seasonality is also not really easy to catch, but convolutions, they really need to handle, the noise residuals of the signal. So I added the layer that estimates the seasonality components and subtracts them from input and adds them to the output. And then it was again better. And then at the end of the day, I also tried to remove the convolutions, and it worked even better and like 10 times faster. And this is how like the base architecture kind of came into being. But also then we analyzed, during the sessions with the collaborators, including Yoshua Benjo, we started analyzing how that architecture is different from what is out there, how it's different from like the general things that could be done. And like, is it really necessary to have those trend removal, seasonality, and whatnot? And Yoshua pretty much suggested that you don't really need to have those trend removal and seasonality layers. You can just learn all of it in one shot. And we implemented the model that doesn't rely on any, predefined layers like trend or seasonality, and that still worked exactly the same, somewhere a little better, somewhere a little worse, but performance was essentially the same. And then at that point in time, we realized that we can learn time series model with no domain knowledge at all. And then at the same time, if we really want to have an interpretable model, we can have those extra layers designed by human whatever specialists that have some domain knowledge and have convenient ways of representing those signals understandable by other people. So like that's how pretty much the synthesis of entire N bits came along, I think.
We talked a little bit at the beginning about the M4 and other M competitions, not just the data sets they provide, but that it's a challenge and we can benchmark algorithms against one another. Can you talk a bit about how NBeats performs in that competition?
Well, I would say that, first of all, it's important to note that NBits didn't really participate in M4 competition because we only started working on that problem half a year or like a year after the M4 competition results were out. I mean, actually, like exactly the results of M4 competition kind of drew my attention to that problem, in addition to the fact that I was working on similar problems while being at Element AI with some of the clients. They were interested in retail forecasting and whatnot. So there was general interest from the industry in that topic, but also M4 was a really nice benchmark. So we decided to use it to develop a model that could then be used, in other applications using that benchmark.
What was the state of the art then as you were looking into M4 before NBeats was developed?
Yes, so the state of the art was the model developed by Slavik Smil, who actually participated in the competition, and his model was a heavy ensemble. I think it's like 90 models in ensemble, which is kind of the same order of magnitude in terms of complexity as NBits. But the basic architecture was like really different. It was based on a combination of the recurrent neural network and the classical approach, where the classical approach was used to remove trend and somehow normalize the data, and the residual stack of RNN models was used to model the residuals from that. So that was the state of the art. So we kind of already know that there are deep learning models that work well on those time series data. But I think one of the conclusions that was made based on M4 competition in the publication that was describing the results, the conclusion was that the only or like the most promising way forward to develop machine learning architectures for time series is to do hybrid approach where you combine some deep learning with some classical statistical models. So like on our side, what we wanted to test is whether we can actually develop a model that is completely deep learning with no time series domain expertise or strings attached to it.
Good challenge then, yeah. So we've got a nice benchmark, even though the results have come out. Tell us a little bit about how NBeats would have performed had it made it into the competition.
Well, I definitely have no idea about that. And I mean, it's always a challenge like working in the competition because the time is limited. Like in our case, the development of NBeats, I think it took about, I don't know, 5-6 months together with paper writing. I'm not sure if we would be able to do it, in time for the competition. If we were like in that strict like competition deadline environment and whatnot. And like results of those competitions, they're always unpredictable. So like what I can talk about with certainty and based on the data is that NBits was used in M5 competition, which was about multivariate time series forecasting. And the model that used NBits scored the second in M5. And actually, like the most, I guess, interesting part of it is that it was used by a completely like different person unrelated to our research group, which makes the results even more valuable in my view, because it's like competition framework, only validation set is available, test set is undisclosed. A person that is using the implementation of NBits from a repository, as far as I understand, it was done by Amazon. There was this repository that I don't even remember right now the name. But anyways, so the person took that implementation, used NBits to forecast, higher aggregation levels of a multivariate time series, and then used another model to predict at the higher resolution levels of those multivariate time series. Combined NBits was that another machine learning model, and the result was second in that competition. I think it really proves that NBits works, and that's not some kind of overfit to a particular benchmark or data set. Even though, I mean, we benchmark on a number of data sets, there is always a risk, like especially people from time series community, when the time series, like the NBits results were first out, they were really skeptical about those results because they said, you guys had access to all the data. Maybe you used test data to overfit. But I mean, this is not how we do, research. So on our side, I was really super sure and clear that NBits is a good architecture. It's not overfit or whatnot. But I mean, it's really hard to convince people with only words. At least in M5, there was a concrete example of using it in competition, and it worked, and that's good, I think.
Yeah. It's wonderful to see a reproduction like that. To your point, yeah, could there have been some accidental leakage? Now you can say for certain on a brand new data set.
Exactly. I mean, we always take those leakage issues very seriously, splitting data sets such that there is the really super minimal risk of ever doing things in the wrong way and using, some of the test data somehow to drive model development. So there is clear division train validation test. We train on the train, hyperparameters on validation. We measure metrics on the test and report them, but there is always a chance. So right now we know that there is no chance for it.
NBeats can be run in, I guess, two sort of modes. The interpretable mode, where the parameters are constrained in a way where I can directly read what those parameters are, or the generic mode. If I'm in a situation where the interpretability isn't critical to me, do I get a performance boost by selecting generic, or I guess what's the difference in performance-wise?
I would say I don't see any statistically significant difference between the two.
So speaks, I guess, in favor of the interpretable model running most of the time, I would guess.
Well, I mean, so because we proposed only trend and seasonality, but there could be, I guess, time series of other types that could have some of the things that are not covered by those two, in which case you are risking, using representations that are not suitable to describe things that are more complex, and then you'll get performance degradation. Whereas the non-interpretable model, it will try to learn the best representation of time series, irrespective of the nature of those.
Do you see any avenues of important future research? Do we have, the final version of NBeats, or do you think there'll be iterations that make incremental gains in different directions?
Sure. Well, first of all, the NBits is really super heavy in terms of computation, and using different techniques to make it more computationally efficient is definitely a direction of incremental improvement. So you could imagine, let's say, trying to reduce ensemble size, somehow making ensemble members more diverse and getting better performance with less models. Then there is definitely a limitation of the model that it takes like constant size inputs and produces constant size outputs, meaning that the forecasting horizon is really fixed. So like we train on, let's say, monthly data, forecast 1 year ahead, and then our model can only produce forecasts 12 months ahead, right? So that's definitely a limitation. Sometimes you want more flexibility. Same was the input window sizes. Let's say we do in the paper, as far as I remember, like from 2 horizons to 7 horizons, something like that. And we process kind of windows of different lengths, but those lengths are fixed. And then for a particular application, you will have to experiment what kind of window sizes need to be used. So if you can eliminate that part from the equation, that will make things a lot simpler and more flexible. Then there are things with multivariate forecasting, and BEATS is really a univariate model, and how to embed multivariate forecasting paradigm, to me, it's not super clear. So I'm not sure if we have to go in the transformer world with all the square complexity of computation and whatnot, and being able to handle multiple time series at a time, or we could advise probably some versions of NBits that will be less computationally heavy, but will be able to handle multiple variables effectively. What else? Like the NBits is a point forecast model, whereas like in many practical situations, we really want to be able to draw samples from the model, estimate quantiles, or even like proper joint distributions. We want to simulate, how things could develop in the future, do risk analysis and other things. So in that case, NBits will not really do the job, but it should be relatively easy to extend it to be able to handle that type of problem.
And as you mentioned a little bit, it can be somewhat heavy in some sense. If I'm observing some very trivial, simple process where a moving average is the best underlying model, I can just go with the moving average. Is there a way researchers or people in industry who are considering whether or not NBeats is appropriate for them could run through some checks and decide if it's the right tool?
Yeah, I think it totally should be the case. You can do model selection just the way it's done in classical time series forecasting all the time. At the same time, in practical terms, like if your data set is small and your compute is limited, then it makes sense. But if your data sets are huge and you have unlimited compute, I think it would be probably a good idea to just always use some neural model and avoid, that selection of models, additional problems and whatnot. At the same time, from the cost perspective, it might be a good thing, to use simpler models where you can and save on the cost of training and inference. I don't know. So it's really like engineering design choice, I would say. And it's really hard to provide any super general guidelines there.
Well, luckily, users have pretty, in my opinion, easy way to just go out and try it. You'd mentioned that Amazon had done an implementation. I think I've probably seen a couple others on GitHub as well. If someone was really interested in getting their hands dirty, do you have any advice for how they should get started?
I would say that the way I usually work is like I find an interesting problem that has reasonably clean data collected for that problem. And I just try to apply a few different techniques to that problem. And then at some point, when you play around enough with that problem, you come up with your own ideas. And like, so it's a way to learn from others.
Well, I was actually kind of asking about more from like a software side. If, let's say, my job has a time series problem and I'm ready to go and show my boss something impressive and I want to try NBeats, got TensorFlow installed, what's next?
Well, I would say that you get the data set and the feedback from the business people who have good visibility on, how the benefits in forecasting accuracy translate in the dollars earned, how this happens. So you get information from the business people, then you get the data set, you get a few implementations of the model because like some of them may be better than others and also could be better for some specific problems than others. So it's always a good idea to try different implementations. So you apply to that problem, get the results, and hopefully you can prove that the accuracy benefit that you get translates in reasonable offsets in terms of the money you can save with improved forecasting.
And there's one topic I wanted to go back and revisit. We've touched on some of the basic ideas, but I don't think we called it out specifically, and that's the topic of meta learning. Maybe for listeners who haven't been introduced to it, could you give it a rough, casual definition? What is meta learning?
So meta learning is learning to learn. And we can think about it in evolutionary terms, for example, like there is a population and individuals in the population. And so there are two training loops going on in that population in terms of, learning to learn. So there is inner loop where each individual in the population over their lifetime, let's say, learns how to solve different problems in their lives, let's say find food or like shelter during rain and things like that. And so the probability that an individual survives depends on their ability to solve those problems. And then this is the inner loop of learning. And then the outer loop happens at the population level where the population optimized in such a way that when the population goes over generation, the individuals in that population become better and better adapted to the conditions of the environment. And so that outer loop makes sure that the next generations, the individuals, they resolve the problems faster and better. And you can think about the same thing in the neural networks. Typically, the meta-learning approach is when you have the thing that is called a learner that is, let's say, a small neural network that can resolve simple tasks. And then there is an outer loop where that network is optimized such that when it's presented with a completely new unseen task, it can use the background knowledge accumulated over multiple tasks to solve that task, but also can adapt to this task really quickly and understand how to use previously accumulated knowledge to resolve that new task. Does it make sense?
Yeah, definitely. Can you then frame meta learning in the context of NBeats?
Yeah, sure. So NBeats consists of residual blocks. And so in the follow-up paper, that we published in AAAI conference, we tried to show that the individual residual block in NBeats is the instance of that learner or individual in the population. And then when you connect or stack many of those blocks, what happens is that this kind of learner, it modifies its own inputs because if you remember, there is a backcast connection. So the learner at stage, let's say k-1, modifies the input to the learner at stage k. And so stage k processes the input signal in a little bit different way than it used to do it in the k-1 block. And so that, from our perspective, incarnates the concept of adaptation. So the individual block in NBeats iterates over the signal and adapts its own operation based on what it sees in that signal. So that forms the inner loop in the meta-learning. And then the whole architecture is learned over multiple time series. So it's optimized over multiple examples, it's optimized how to adapt better to those individual signals. So that forms the outer meta-learning loop. And we showed actually that when you share parameters across all the blocks in n bits, it still performs in pretty much the same way. There is really only a little bit of loss in performance, and sometimes there is even like gain. And so we concluded that this can only be achieved if the block that is repeated really adapts to the input.
Very cool. Well, that's ideal for a lot of the time series cases I've looked at. Are there any areas you think NBeats should probably be applied to, like industries or use cases that maybe people are under expecting? Are there opportunities in finance or agriculture or things like that that are interesting?
I would say agriculture definitely is the case where we can use it. Finance, I think what we saw previously during our limited experiments was that sector is that it's really all about multivariate forecasting. So we really need to have multiple signals, look into those signals, and preferably if the preferable application scenario is when we have covariates that also are available in the future, and then we can extrapolate much better. And univariate forecasting for finance, I'm not sure how much juice we can get out of there. And the other thing is, whenever we have really super strong seasonalities and trends, but also a lot of noise on top of them. So this is where the ideal application area where I can see, NBits being super useful. And that covers a lot of interesting cases, like, for example, the electricity forecasting. There was a recent collaboration with the guys from Poland, and we published a study in the Journal of Applied Energy where we showed that NBits can be used very effectively for electricity load forecasting, and in a very small data regime where we have just a few dozen of time series, and still we don't really have significant overfitting problems or whatnot. And bits showed really promising results. Then Internet of Things and sensor data was lots of different seasonalities. This is where I see NBits can be really very useful. Also, the green energy, predicting the supply of energy from volatile energy sources. But when they have well-defined seasonalities over, year and over, let's say, day and night, things like that. So agriculture, Internet of Things, electricity, and green energy, I think those are the areas where I can see things being really much improved by using NBits.
Yeah, exciting opportunities there. What's next for you? Are you still actively engaged in research, either professionally or casually, or things like that?
I'm really actively engaged in research professionally because research is what I do at Unity. And we have very unique environment where we can publish results of our research, because pretty much we develop the tools that people use to develop games with Unity. And so the more open source tools we develop, the better for the company. And that means that the more we can publish, the better, which is pretty unique. And I'm still working on some of the sequence modeling issues and time series, but it's more in the context of modeling characters in the games. And it's actually a more interesting problem in the sense that it's time series and also, a graphical representation. And, we have to represent the body and the body motion in time. And there are all of the exciting aspects of it that are related to how we model physics and how do we marry physics and machine learning, and do we do planning. So there is this, aspect of models that have to be able to model distributions rather than point forecasts and things like that.
And is there anywhere people can follow you online?
I have Twitter and LinkedIn, I guess. And Twitter is B. Oreshkin, and LinkedIn, it's Boris Oreshkin.
Excellent. Well, we'll have that in the show notes. Well, Boris, thank you so much for taking the time to come on the show and share your work and expertise.
Well, it's totally my pleasure. Thank you so much, Kyle, for inviting me. And it was a great pleasure to talk to you.
Thanks for listening to another installment of Data Skeptic Time Series. Our guest today was Boris Oreshkin. Myself, Claudia Armbruster, as associate producer, Vanessa Bly does guest coordination, and our host, Kyle Polich.